this video, we will see a problem of calculation of maximum height for a chimney. Here is the question. A circular chimney, 2.5 meter internal diameter and uniform thickness of 0.575 meter. Whatever is given here, I'll write that in the form of data by reading the question. Here it is given that there is a circular chimney, 2.5 meter internal diameter. So internal diameter is denoted by small d and uniform thickness of 0.75 meter. So the thickness is taken as t, 0.75 meter. Then is subjected to a horizontal wind pressure of 1 kilonewton per meter square. Wind pressure, I'll denote it as P suffix W, 1 kilonewton per meter square. So it is 10 raised to 3 Newton per meter square. Next, find the maximum height to which the chimney can be raised to have no tension anywhere at the base. It means we have to find the maximum height. That height I'll denote it as capital H. That is the height of the chimney. Next, so that to have no tension anywhere at the base. So the condition is no tension condition. Next, the masonry weighs 21 kilonewton per meter cube. This is the weight density of the masonry. That is another word for chimney. So it is 21 kilonewton per meter cube. So that is 21 into 10 raised to 3 Newton per meter cube. Then find the stresses developed at the base. Assume coefficient of wind resistance as 0.6. So we have to find out stresses at the base, that is sigma max and sigma min, and the wind resistance is denoted by C, that is given as 0.6. So now with the data available, the next thing is I can start with the diagram. Here as we see small d is given, we can even get small d from here. I can get capital D as small d plus twice into thickness. So therefore capital D will be 2.5 plus 2 into 0.75. So therefore capital D comes out to be 4 meter. Now with the data available, let us try to get the solution to this problem. And in the solution, first we need to draw the diagram. It is clear that here we have capital D and small d, outer and inner diameter. So the section is a hollow cross section for the chimney. Now here in the solution part, first I'll need to draw the diagram. Now here we have the hollow cross section. This is the hollow cross section of the chimney. Now I'll project this upwards and get the height. So here we have this height of chimney, which I'll denote it by capital H. And here, since the section is hollow, I'll project the inner circle as well. So now this is the given chimney, or we can say the masonry wall is the other word. Now here in the problem it is mentioned that it is subjected to a horizontal wind pressure of 1 kilonewton per meter square. So I'll assume that the wind pressure is acting on one side of the masonry wall. So here this is the front view of the chimney where we have the wind pressure, and this is the top view in which we will see it as a hollow cross section. P suffix W, it is 10 raised to 3 Newton per meter square. So here is the wind pressure. Now the question is to find the maximum height of this chimney, and for that they have given some no tension condition. First of all, once we have the values of external and inner diameter, we'll calculate the cross section area. So in the problem I'll start with, since the cross sectional area of given chimney, it is capital A is equal to pi by 4 outer diameter square minus inner diameter square. So here we have pi by 4. Capital D is, we have found out, it was 4 meter and small d is 2.5. So from this I'll get the answer of area as 7.66 meters square. Now after getting the cross section area, in this problem they have given the weight density of the chimney. From this we will calculate the weight acting because of its self weight. So now I'll write down that since load on the chimney because of its self weight is given by the load, I'll denote it as W, and it is given by weight density multiplied by the volume. So therefore capital W is equal to weight density is given as 21 into 10 raised to 3 Newton per meter cube. 21 into 10 raised to 3. Volume is, it is area into length, or here it will be area into height. So once we have the cross section, we'll multiply the height to get the volume. Area was 7.66. Height, I'll keep it as capital H because we don't have the value of this height. Now this term I'll keep it as it is because this is the total load acting. And now because of this total load, there will be compression produced because of the self weight of the chimney. We can say that the load is axial owing to the self weight, and because of this there will be direct compression of this chimney. So I'll write down, hence direct stress induced because of self weight, that direct stress is weight upon area so therefore direct stress is equal to weight is 21 into 10 raised to 3 into 7.66 into capital H divided by area. Area we have found out it was 7.66. So this 7.66 gets cancelled out, and here we have direct stress is equal to 21 into 10 raised to 3 into capital H. I'll denote it as equation number 1. Now, after getting the direct stress, since in the problem it is given that there is wind pressure acting on one side, so because of the wind pressure there will be wind force, and because of that wind force there will be bending of this chimney in the direction of wind, and because of that bending stress would be induced. So first we need to know the value of this wind force. We have wind pressure, so I'll say that since wind force acting on one side of the face of chimney is given by wind force, I'll denote it as F suffix W, and that is wind pressure multiplied by projected area. And projected area, it is that area on which the force is acting, and that area would be, as we can see from the top view, the wind would be contact only up till this region. This is the outer diameter and into this height. So outer diameter into height, I'll draw it here to explain it in a more better way. This is the height, capital H, and here we have capital D, or the outer diameter, and this area is nothing but the projected area, diameter into height, on which the wind force is acting. So therefore F suffix W will become, wind pressure was 10 raised to 3, it is given in the problem, 10 raised to 3 Newton per meter square. So 10 raised to 3 into projected area is D into H. So therefore wind force becomes, here D is 4, so 4 into 10 raised to 3 multiplied by H. Wind force, we'll assume that it is in terms of Newton. Now after getting the wind force, this wind force acts at a distance of h by 2 from base, or we can say h by 2 from top, so it is acting directly at half of the height. So here we have the wind force, and if I take the moment of this wind force, then this will be Fw into h by 2, and because of that there will be bending. So I'll write down after this, therefore bending moment produced because of wind force, that bending moment will be wind force into h by 2, because we know moment is force into perpendicular distance. So here wind force it was 4 into 10 raised to 3 multiplied by h, and here I have into h by 2, so it becomes, here we have this value as, and in this problem here, since even they have given the wind resistance that we have to use, so here it was given that assume the coefficient of wind resistance as 0.6, so we have to use that coefficient of wind resistance and multiply it here. So I'll write down in this term we are even multiplying by c, that is the coefficient of wind resistance, it is 0.6. so after getting this, the bending moment calculation, it comes out to be 1200 h into h, that is h square, and here the unit is Newton meter. Now once we have bending moment, the next thing is to get the moment of inertia for the section, and for that I'll write down, since mi about vertical axis is given by I is equal to, here we have hollow circular section, so the moment of inertia is pi by 64, capital diameter raised to 4 minus small diameter raised to 4, so pi by 64, capital diameter is 4, inner diameter is 2.5, so here I get the value of I value comes out to be, it is 10.65 meter raised to 4. Now after getting I, this moment of inertia we had calculated about the vertical axis, and the distance of this vertical axis, this is nothing but y, so it is capital D by 2. So here I'll say that therefore y is equal to capital D by 2, capital D is 4, so y becomes 2 meter. After this I'll say that once I and y values are there, so therefore section modulus for given section, and since it is a hollow rectangular section, z is equal to I upon y, so therefore putting the values here, I was 10.65, y is 2, so therefore z will be 5.32 meter cube. After getting z, previously we had bending moment, now we have section modulus, so therefore bending stress induced because of wind force, that bending stress is given by sigma b is equal to m by z, so therefore sigma b is equal to m, it was 1200 into capital H square, z we have found out just now, it is 5.32, so therefore bending stress comes out to be, if I calculate this, 225.56 into H square, and the unit is Newton per meter square. Now once we know bending stress, in the problem it was given that there is no tension condition, so I'll write down, since for no tension condition means only compression should be there, so for no tension condition direct stress is equal to bending stress. So therefore previously we had calculated direct stress was 21 into 10 raised to 3 H, bending stress 225.56 H square. I'll say that refer equation 1. There we have direct stress. Now from this, here we can see that 1 H and 1 H gets cancelled, so only H remains. So finally, therefore capital H is equal to 21 into 10 raised to 3 divided by 225.56, and I'll get my answer as 93.10 meter. So this is the answer. Now, as mentioned in the question was, for the conditions given, calculate the maximum height of chimney. It is 93.10 meter. So I can say that therefore the maximum height of chimney under given conditions is 93.10 meter. And once we have found out this value, we can say that the problem has been completed.